In an attempt to better understand the advanced chemical recycling of polymers, we would like to explore some of the technical intricacies of the thermal decomposition of different types of plastics. The thermal process utilizes high temperatures, or heat, to break down the complex long-chain polymers into simpler elements and compounds. Not all plastic chemistries are the same, so we will attempt to classify different types of plastics into a few broad general groups. The first grouping of plastics contains the simple hydrocarbon bonds, like olefins or polyolefins. This type of plastic primarily includes different combinations of only carbon and hydrogen molecules, and excludes any other elements. Examples of simple hydrocarbon materials include polypropylene, which has a chemical formula of C3H6, polyethylene that is, C2H4, or butylene, with a formula of C4H8, and also a simple aromatic monomer like polystyrene, whose formula is C8H8. These simple hydrocarbon molecules repeat and link, forming a repetitive long chain, or a polymer. The thermal reduction of simple hydrocarbon compounds breaks these chains, and results in the production of some combination of just either carbon or hydrogen. The second grouping of plastics adds oxygen to the hydrocarbon bonds, forming a carbon-hydrogen-oxygen molecule. One example of this type of plastic is known as polyester. The most common form of polyester is PET or PET, polyethylene terephthalate, which has a chemical formula of C10H8O4. Another form of this group of plastic is polymethyl methacrylate, PMMA, which is commonly known as acrylic or plexiglass, whose formula is C5H8O2. We also encounter POM or POM, polyoxymethylene, commonly known as acetyl or acetal, which has a formula of CH2O. Also in this second grouping of plastics we see phenol, C6H6O4, and bisphenol A, BPA, commonly found as polycarbonate and epoxy resins and identified as C15H16O2. The thermal reduction of hydrocarbons, with the presence of oxygen, may produce a combination of carbon or hydrogen, and a mix of carbon oxides and water. The next, or third group of plastics, become more complex, by including additional elements such as nitrogen. This group may include nylon or acrylonitrile. Common examples such as nylon 6, C6H11NO, or nylon 6,6, C12H22N2O2, include nitrogen in the molecular matrix. We also encounter acrylonitrile, C3H3N, which adds chemical resistance, hardness, and thermal stability. We most commonly find this material as a mixed compound such as ABS, acrylonitrile butadiene styrene. The thermal reduction of hydrocarbon compounds, that contain oxygen and nitrogen, may also produce ammonia, cyanide and NOx byproducts. Other complex compounds and plastic molecules, that may include polymers such as polyvinyl chloride, PVC, which has a chemistry of C2H3Cl, contain chlorine in the matrix, and other groups like fluorinated polymers all add complexity to the recovery process. These elements must be properly dealt with, in additional processing steps, since the reduction of these complex compounds produces acid gases in the byproducts. In addition to segregated homogeneous polymer resins, we encounter mixed plastics, multi-layer wastes and laminated materials. Other foreign residual materials may be derived from inert additives, fillers and colorants and will collect as residues in the thermal-chemical plastic recycling process. A robust, multi-stage process must be designed to adequately handle these mixed complex materials and the associated residues and byproducts. Now that we have classified the types of plastics into some general groups, we may now address some of the concepts of advanced chemical recycling and thermal processing methods. Partial decomposition, or partial depolymerization, breaks a large molecule or polymer down into smaller, still useful molecular chains, such as oligomers or monomers for potential reuse. Full reduction, or full decomposition of plastics, destroys the original molecular structure entirely, reducing it into basic elements or simple compounds such as carbon and hydrogen along with CO2 and water. You must be prepared to endure the energy penalty if you wish to achieve reduction into basic elemental building blocks. Near full reduction results in the production of an intermediate product, such as syngas, which contains some mix of carbon oxides like carbon monoxide, or carbon dioxide, hydrogen, water, methane or other hydrocarbons and some residual elements. Once you reduce the hydrocarbons back into basic, or near basic elemental building blocks, you may chemically reconstruct these elements or molecules into whatever compounds or products you desire. Chemical conversion or syngas synthesis may be used to produce a wide variety of chemicals, plastics or fuels. E-fuel, and liquid hydrocarbon fuels such as methanol or ethanol, may be used as liquid fuel blends or directly as drop-in substitutes to traditional fossil fuels. The development of sustainable aviation fuel, produced from regenerated wastes, is an active area of interest. The use of waste materials as a source of regenerated energy, in the form of recovered synthetic biofuels, may act as an offset of a carbon footprint balance, to become a carbon-neutral fuel. Hydrocarbon cracking, or syngas reforming, to convert light hydrocarbons like naphtha into olefins may be a fundamental platform to the production of regenerated plastics. The combustion, gasification or pyrolysis of plastics, hydrocarbons, or other waste materials in a thermal reduction process, that fully contains the emissions, and utilizes or converts those would-be emissions, into a resource for the source feedstock to produce chemicals, plastics or fuels, is the basis of a sustainable circular economy. Containing elements in a regenerative loop, may eliminate or avoid undesirable emissions altogether, while maintaining a neutral equilibrium or an environmental homeostasis. Establishing a regenerative environmental equilibrium is an energy-intensive process, and requires a continuous energy input in order to be maintained. The methods we choose to generate, convert and recover energy may be key to a sustainable future. How we augment the regenerative energy deficit is a critical component in a successful strategy and may require true innovation. In regard to the thermal heat source required to drive the thermal-chemical plastic reduction process forward, we are presented with multiple options that we intend to discuss in greater detail at some point in the future. Until then, please feel free to contact us at your convenience if you have further inquiries. Please visit us at www.waste.net.